Welcome to lecture number 29. So we are discussing the direct method for transient stability analysis. So as already we have discussed how to, already we are talking about little bit how we'll do the direct method analysis and how it is beneficial. Already we discussed direct method is very fast and we can assess the stability very quickly, and generally it is used for dynamic security assessment DSA tools. So these things we have discussed, and we are talking about the modeling issues. How we'll model the system uh, to assess the uh, dynamics or assess the transient stability using the Lyapunov method. That is how to derive the energy function, how to find the critical energy function, then how to find the critical time as well, critical clearing time, all those things. So let us rewind it, the modeling issues. So in applying the TF technique, we must consider the model in two time frames. Already we talked in the last class. The faulted system can be represented like this, and that is FFXT, and then post fault system we can represent, that is in another time frame, that is from time that is greater than TCL. Then in reality the model is a set of differential algebraic equation. So already we know this, and we can represent those differential algebraic equations in this manner. One is the set of differential equations, set of algebraic equations, and the time frame is 0 to TCL. And next one is your for other time frame, which is from t greater than TCL, that is under post fault condition. So the function g represents the nonlinear algebraic equation of the starter and the network, while the differential equation represent the dynamics of the generating unit and its control. Already we know this, and we need to understand whether a more detailed generator or load model will lead to more accurate estimate of TCR, or only by classical model it is fine. So in the literature already it is studied, many researches have been conducted, and it is found that for the so-called first swing stability, that is instability occurring in 1 to 2 second interval, the classical model with the load represented as constant impedance will sufficient. So this results in only differential equations as opposed to the DAE. So therefore we don't require here the differential algebraic equation. Instead only we can consider the differential equation, because the classical model we know it is represented by the differential equation itself. So we can represent the differential equation, and when we'll consider the load as the impedance load. So both the PEBS, that is potential energy boundary condition, and the BCU, that is the BCU is boundary controlling on equilibrium stable point method, that gives satisfactory results for this model. So for this classical model, so we are not going to discuss the lowest energy unstable equilibrium point method. So let us discuss this in the multi-machine context. So we'll formulate a generalized approach, then we'll discuss the single machine infinite bus, and because single machine infinite bus is more appropriate to discuss all the time, but we cannot very go deep into multi-machine context. So we'll formulate a generalized approach for multi-machine context, then we'll go detailed discussion we'll do for single machine infinite bus system. So this is the formulation we are doing for the multi-machine system, right? So for multimation system, we can write the differential equation for the classical model like this. Already we did this. So P is nothing but your electrical power output from generators, and there are having m number of masons. So already we talked here, like PI is equal to EI square GII plus j equal to 1 to m, which is not equal to I, Cij sine delta ij plus Dij cos delta. So last time you questioned regarding this, how this expression came. So I'll talk about this, how the derivation came. So we'll denote here 2hi by omega s equal to mi and pi equal to pmi minus ei square gii. So then we get this expression. So mi d square delta I by dt square plus di d delta I by dt equal to pi minus the rest of the terms. And final expression will get this expression, that is pi as function of delta I to delta m. And this is in fact given in the book MA Pi. So I got this in section, if you'll refer to section 6.6, that is multi-mason classical model in MA Pi. The details is given. So briefly we'll discuss here how the expressions derived. So 2hi by omega s into d omega. So this is the expression. We know this is the expression when we derive for the classical model equation, that is TMI is the torque, mechanical torque input minus real part of this expression, that is voltage and current multiplication, and this term is your damping factor or damping torque, you can say. So it is for all the masons mentioned. And from this already we know that the current we can write, if it is the network is represented, and along with the network and the load represented as the impedance load, we can write the current in this manner. So this G dash rad plus JB dash rad is nothing but they're the reduced Y-bus matrix. Already we did this in the earlier classes, how to reduce a Y-bus matrix to the internal node of the generators. So this G rad dash IK plus JB dash rad IK is the ikth entry of an M by M admittance matrix, and it is often called the matrix reduced to internal nodes. Already we discussed this, how to reduce the uh, Y-bus matrix, which is defined in a network. If a network is of size n by n and you have m number of generators, then we can reduce the Y-bus matrix to m by m. So already we have discussed this, so we are not repeating here. So we can do this, and defining the delta classical equal to delta I plus delta I dash naught, that is for I equal to 1 to m. So then we can write that the final expression of this equation can be written in this form, that is 2hi by omega s d omega I by dt equal to tmi, and the expression for this, which can be expression for this can be written in this form by substituting the current expression there. By substituting this current expression here in this, we'll find the final expression, right? So it is very easily we can see that this cos of delta classical I and delta classical k, they are nothing but delta of ik we represent, sorry, delta of ik. So here also it is delta ik. So it is naturally we can represent the expression. So now we can write the equations in this form. So if we'll write pi, so pi I can write, because the pi is here from here to here. Okay, So I can write this Pi in this form. So when j equal to I, your the term will become Ei square Gii, and other terms will be, so Cij and Dij, they are the constants. They are represented by these terms. This is Cij and this is Dij. Okay. So now the expression can be written. I hope everybody understood these expressions. So now we'll go ahead. So 2hi, the same expression what we discussed, denoting this, and finally already we know, we'll go by this, and then we got this expression, right? Then we can write the state space model for this system as this. The state space model will be delta I dot equal to omega I minus omega s, then omega I dot equal to 1 by mi, pi equal to pi as a function of delta 1 to delta m minus di omega I minus omega s. Now where omega I is the angular velocity of the rotor and omega s is the synchronous speed. So omega s is the synchronous speed in the radian per second. So it's okay. So above equations are applicable both to the faulted state and the post-fault state, with the difference that Pi is different in each case. So Pi will be different for faulted case as well as post-fault case, because the configuration, the network configuration changes. So therefore Pi, the expression for Pi, the equation for Pi will change, because of the internal node admittance matrix is different for the faulted and post-fault system. So the model corresponding to these equations is known as internal node model. So this model is known as internal node model, since the physical buses have been eliminated by the network reduction. So physical buses are not there because it is already eliminated and the Y bus matrix is reduced. So now let us see how to formulate the energy function. So it is very important. So we'll generalize this formulation, then we'll go ahead. So prior to 1979, there was considerable research in constructing a Lyapunov function for the system represented using state space model given by this. Already the state space model we have. So there are ample number of literature available, and they have tried to formulate the energy function using this state space model. So we have two options to use: either the relative rotor angle formulation. So there are many literatures also there which have used the relative rotor angle formulation, and another option is the center of inertia formulation. So what is relative rotor angle formulation? That the relative rotor angle formulation means each machine will have the relative angle with others. That is the relative rotor angle formulation. But the center of inertia formulation is that we have to find the center of inertia, and with respect to that we have to find the relative rotor angle. So we'll consider this the COI formulation here. This is, since there are some advantages of this formulation, we call it COI formulation, that is center of inertia formulation. Since the angles are referred to a center of inertia, the resulting energy function is called the transient energy function. It is also known as transient energy function. In this formulation, the angle of center of inertia is used as the reference angle. Okay, so here in case of relative rotor angle formulation, we choose some reference bus or reference machine. With respect to that we do, but in case of center of inertia, we calculate the center of inertia angle of center of inertia, then we consider that as the reference angle, since it represents the main motion of the system. So therefore it plays very important role, because this center of inertia angle or center of inertia it represents the main motion of the system. So then what is this center of inertia? Although the resulting energy function is identical to V delta omega. So this energy function is represented by B delta omega using the relative row triangles. It has the advantage of being more symmetric and easier to handle in case of center of inertia method. So synchronous stability of all machines is judged by examining the angles referenced only to CY instead of the relative row triangle. Therefore, modern literature invariably uses the center of inertia formulation. So whatever modern literatures are coming, so it is very important, those who are doing research in power system stability, that the center of inertia formulation is important for them. The energy function in COI notation, including Dij terms, that is the transfer conductances, was first proposed by Athai et al. So COI including this, generally these transfer conductances were neglected in many research papers because of the ease of analysis and formulation. But this is the first author who proposed this COI formulation using these Dij terms, which are nothing but the transfer conductances. We'll derive the transient energy function here for conservative system, assuming di equal to 0. Di equal to 0 means there is a difference between these two terms. You should mark Dij and Di. So Dij is not equal to Di. Di is your damping factor, right? So damping factor here is assumed here 0 for simple analysis. The center of inertia for the whole system can be defined as this. This is the angle of center of inertia, delta naught, that is equal to 1 by mt, sum of I equal to 1 to m, mi delta I. So what is this mt? And mi is nothing but the moment of inertia, mi, of each machine, and the center of speed, that is omega naught, can be represented as 1 by mt, sum of the mi omega I, multiplication of mi omega I. So what is this mt? Mt is nothing but sum of the mis. So that is sum of all the moment of inertia of all the machines. That is mt. That is total moment of inertia of the system. So we then transform the variables delta I and omega I to COI variables. Like we transform the variable to synchronous frame of reference, here also we can transform this delta I and omega I to COI variables. Like that, I can write theta I, I'll define theta I equal to delta I minus delta O. Like I write delta I equal to theta I plus delta O. Previously also we did like this for synchronous frame of reference. So similarly, omega I tilde, I can write omega I minus omega naught. Okay, so and now by substituting theta I in theta I dot, I can write theta I dot equal to delta I dot minus delta O dot, that is equal to omega I minus omega O, which is nothing but equal to omega I tilde. Okay, so therefore theta I dot is equal to omega I tilde. The swing equations with di equal to 0, that become, considering di equal to 0, now the swing equation I can write is mi d square delta I by dt square equal to pi minus summation of Cij sine delta ij plus Dij cos delta ij. So inside the pi we have another term, that is Gii. So that one term when j equal to I term is added here with pi. So substituting delta I equal to theta I plus delta O here in this equation, just substitute in this equation, substituting what we'll get, mi d square theta I. So each of the delta I will be substituted by theta I plus delta naught. So it will become mi d square theta I by dt square plus mi d square delta O by dt square equal to pi minus this, the rest of the terms. Then substituting delta O equal to, we know this 1 by mt, summation of multiplication of mi and delta I. Substituting this in this equation, instead of, in case of delta O, we'll get this term. Okay. So now we'll get mi d square theta. So after substituting, we'll get this one more term, that is mi by mt, sum of mi d square delta by dt square. So now just substituting this term instead of mi d square, instead of mi d square delta I by dt square, just substituting this. So you will get this expression. So the expression is mi d square theta I by dt square equal to pi sum of cij sin theta ij plus dij cos theta ij, j 1 to m not equal to I, minus mi by mt multiplied with pi, which we have substituted here, summation 1 to m, and here we have double summation. And now just simplifying this term, the second term of this, we'll get this expression. So after getting this expression, just we'll put this whole term as a constant term, that is known as PCOI. That is, COI is center of inertia. We are representing P. It is a power term, so therefore we are representing it as PCOI. So where your Pi is equal to PMI minus EI square GII, and PCOI is nothing but this term, right? So if one of the machines is an infinite bus, very huge machine is connected to that bus. Let us say the bus number is M, whose inertia constant is mm, and it is very large, then what will happen to the system? So your mi by mt PCOI will become approximately 0 when I is not equal to m. When I is not equal to m, at that point of time, PCOI, when I will be equal to m, so your, this term will not be 0. Okay. So now delta O equal to delta M, and omega O will become omega M because it's a huge machine. So we are substituting delta O equal to delta M and omega O equal to omega M. So the COI variables become theta I equal to delta I minus delta M, and omega I tilde is equal to omega I minus omega M. So we'll consider the general case in which all mi is finite. Considering that, corresponding to the faulted and the post fault states, we have two sets of differential equations. Now this is one set. This is with time frame 0 to TCL. So 0 is the time at which the fault is happening, and another time frame is t greater than TCL. So there is just, it is not, in fact it is another term. Okay, so we should not consider it is single term. This is another term. So it is, there are two equations, mi d omega I tilde by dt equal to fi f theta. So this is the function, and mi d omega I tilde by dt equal to fi theta. So let the post fault system given by the second equation, this is the post fault system, and have the stable equilibrium point at theta equal to theta s. Let us say there is a point theta equal to theta s and omega tilde equal to 0, where there is a stable equilibrium point, post fault stable equilibrium point. And from this equation, theta s can be obtained by solving the nonlinear algebraic equation. So as soon as it achieves the stable equilibrium point, this left hand side will become 0. So then we'll have the algebraic equation fi theta equal to 0. So from this equation we can find theta s. So then also we can find omega tilde. Okay, so we'll see it later for single mesh in infinite bus system. So if I equal to 0 for I equal to 1 to m, and considering delta m equal to 0, if we'll consider delta m, the angle of the uh, Hughes Mason is equal to 0, then your this equation mi theta I will be equal to 0. Then theta m can be expressed in terms of other thetas and can be substituted in this equation. So now we have m minus 1 number of equations instead of m equations. So now we'll have fi as a function of theta 1 to theta m minus 1 that equal to 0, and it is for I equal to 1 to m minus 1. So the basic procedure for computing the critical clearing time consists of the following steps. We have 3 steps. First step is to construct an energy function or Lyapunov function that is represented as v of theta omega tilde, that is the post fault system, and find the critical value of this energy function for a given fault denoted by VCR. So this step is very important, this finding the VCR, critical value of this energy function, and then integrate the faulted system equations, that is V theta omega tilde equal to VCR at the critical point. If we'll equate this and integrate this instant of time is known as the critical clearing time. Already we know in case of equal area criteria how to uh, calculate this TCR. Here also it is somehow related to the equal area criteria. We'll discuss it later. So this is how we calculate by equating these two equations, V theta omega tilde equal to VCR. While this procedure is common to all the methods, they differ from one another in step 2 and 3. Even if they are common for all the methods, they differ from one another in step 2 and 3, that is finding VCR and integrating the swing equations to find TCR. These are the different aspects. So there is general agreement that first integral of the post-fault system equation constitutes a proper energy function. Post-fault system equation that constitutes a proper energy function. So let us see the functions or the differential equations. So this is the differential equation, that is mi d of dt omega I tilde equal to fi theta, and this is for post fault condition, post fault time frame, d theta I by dt equal to omega I tilde. We know this for all the masons, right? Now just we'll equate dt for both the masons, and then we'll consider each of the pairs and find the equation. So let us equate dt from this equation. Dt will be for first mason, dt will be equal to this, and for this equation, from this equation, dt will be d theta 1 by omega 1 tilde for the first mason. Similarly for second mason, and gradually for mth mason we'll find these values. And if we'll equate and we'll consider each pair individually for first mason, for second mason, for mth mason, then integrating the pairs of equations for each mason between theta si 0, this is the point, this is the theta and this is omega, this is the initial point, or you can say the stable equilibrium point, the post fault stable equilibrium point to theta I omega I tilde, the equation will result in this. So from this, if we'll equate and from each pair, if we'll multiply mi d omega tilde into omega 1 I, or generalizing this, I can write this as half of mi omega I tilde square. If I'll integrate this, I can write the equation. You can see it. So the general equation from this equation will become mi d omega I, sorry, mi omega I tilde d omega I equal to f1 fi theta d theta. This will be our equation. Now from this equation you can find the energy function as just taking this equation to that side. So under stable equilibrium point it will be 0, but during fault condition it will be not equal to 0. So we'll represent this expression as a function. That function is nothing but vi theta, vi as function of theta omega tilde, and I can write this expression as, and integrating I can write this expression. The integration period is theta is varying from, sorry, theta is varying from theta si to theta I, and omega tilde is varying from 0 to omega I tilde. Okay, some problem. It will vary from, omega will vary from 0 to omega I tilde, and theta will vary from theta si to theta I. So in order to get a general expression for the energy function, we find this from half of mi omega I square minus theta si integration theta si theta I fi theta d theta I. So this is known in the literature as individual Meson energy function. So this is for a particular Meson. It is defined for a particular Meson, like it has been mentioned, I equal to 1 to m. So this is known as energy function for each individual Meson. Now adding these functions for all the Mesons, we obtain the first integral of motion for the system as this. So your final expression for energy function for the whole system will be summation of all the energy functions for all the Mesons, that is from I equal to 1 to m. So this is the final energy function expression for the whole system energy function equation. Now it can be represented or segregated as two terms. One is the kinetic energy term, other one is the potential energy term. Very nicely we can observe this is the kinetic energy term and this is your potential energy term. So okay, so this is a general formulation of energy function. So now considering this, so we'll step by step analyze. So first we'll discuss the method which is known as potential energy boundary surface method. Okay, potential energy boundary surface method is already we have discussed little bit briefly, but we'll discuss here more clearly. Now a simple example is considered here just to demonstrate the potential energy boundary surface method, PEBS method. You can say you can see there is a bowl. There is a bowl where inside the bowl we have a ball, and that ball is now under steady state condition, and let us say we give a disturbance to the ball. So what will happen to the ball? So it will move in this direction or in this direction, either of the direction as per our force. So if it will move in this direction, then it will not reach to the boundary or the edge of the ball, then it will again come back and it will oscillate between this point, and finally it will settle down at the So this point is known as your stable equilibrium point. So this is your ACP, right? And from ACP, any disturbance you give, so if it will go here, at this point, as soon as it reaches, the potential energy becomes maximum and the kinetic energy becomes zero. But as soon as there is little more disturbance you give here, it will become unstable. Therefore, it is known as unstable equilibrium point. So, when the ball reaches here, the energy of the ball, if we can express or we can compute, that is known as the critical energy of the ball. So, our critical energy can be defined based on the this boundary surface. Okay, so this is the basic principle of the potential energy boundary surface method. That means as soon as it reaches the unstable equilibrium point, the system becomes as the system reaches the unstable equilibrium point, at that point if we can calculate this critical energy, the energy function, or evaluate the energy function, that gives us the critical energy, and based on that we can find the critical clearing time as well. Okay, so this is the potential energy bound basics of the potential energy boundary surface method. So let us consider a single mesh in infinite bus. So in this class we'll not very detailed, we cannot analyze because of the time, less time, but we can little bit go ahead with the system how we are considering. So consider a single mesh in infinite bus system. This system which is connected to the infinite bus through a transformer and two parallel lines having the reactance x1 and here the transformer reactance is xt, and the synchronous generator uh, transient reactance is xd dash, and it is connected to infinite bus. And let us assume that the voltage behind this transient reactance is E1 delta and the infinite bus voltage is E2 0, the reference bus. So now let us say that the fault is at the as one of the line. Let us add this line at the middle of the line. Okay. So a three-phase fault occurs at the middle of one of the lines at t equal to 0 and is subsequently cleared at t equal to TCL by opening the circuit breakers at both the ends of the faulted line. So by opening these two circuit breakers, if the fault is cleared at t equal to TCL, then that will give us the post-fault condition. Now under pre-fault condition, pre-fault system, how it will look like, it is very simple. Just the equivalent circuit if we'll see E1 delta, and here if we'll represent the infinite bus as a equivalent Mason, that is E2 0, and I will connect this J of xd dash xt and jxl jx. This is xl, not x1, xl. So jxl and jxl, just simple by adding we'll find the equivalent equivalent impedance or reactance. So equivalent reactance is xi for the pre-fault condition, for pre-fault system. So now we can find the electrical power output. The expression will be U1 A2 by xi sine delta. This is very simple expression. Now coming to the faulted condition, during fault, when the fault happened at the middle of the one of the parallel lines here. So at that point, what happens? The network will look like this. So it will divide it into two parts, XL by 2 and XL by 2, both are grounded. Now here at this point it is little difficult to find the equivalent reactance or equivalent impedance. So here E1 delta, if we'll find the equivalent impedance, then somehow we'll find equivalent impedance. Let us represent that equivalent reactance as XF, and really it's difficult to find XF. So how we'll find here XF? Just we can see here the star points. If we'll convert this star equivalent to the delta circuit or delta network, then we can add together the parallel circuits and we'll find the equivalent reactance XF. So your P will be the electrical power output will be E1 E2 by, and this is on during fault condition, by XF sine delta, and XF can be computed for this network by performing Y delta transformation. It is easy for this case, this single mesh and infinite bus system, but if we'll consider multi-mesh system, in that case it will be really difficult to find this. So therefore, in case of multi-mesh system, we'll have a generalized analysis how during fault how the impedance how the admittance matrix will be modified. Okay. This is the post-fault condition where the fault is removed and all the reactances are added. The line reactance, transformer reactance, and the generator reactance are added together, and that will give us the final effective or equivalent reactance. And here P will be U1 A2 by X sine delta. So the computation of Xi for pre-fault system and X for the post-fault system is straightforward. However, the computation of XF is cumbersome. So we'll discuss a general method that is applicable to the multi-mesh case as well. So we'll discuss it in the next class and then we'll go forward. So we'll stop here.